Alright, today we're going to finish up section 2.6, 2 quick examples, and then we'll be done. So first, I want you to find a rational function with the following properties. It needs to have a horizontal asymptote of y equals 2, a vertical asymptote of x equals 3, and a 0 of x equals -1. Now there are many correct answers, but I don't want you to make there cannot be any other zeros, there cannot be any other vertical asymptotes, and there cannot be any other horizontal asymptotes. So I wanted to only have these 3 features. So pause the video, try to come up with an answer, and unpause it when you think you have one. Again, there are many correct. Okay, so I'll show you 3 examples that I came up with. The first one here, f of x equals 2 times the quantity x plus 1 over x minus 3. This is the simplest example. You do not need to multiply the 2. You could if you want, and hopefully you understand this is just 2x plus 2 over x minus 3. But in the factor form, it's really easy to see that I'm meeting my requirements of I have a vertical asymptote of x equals 3, 0 is going to be x equals -1, and again, remember that's the x value, it's actually a point. And I have a horizontal asymptote of y equals 2 because the degree of the numerator is 1 and the degree of the denominator is 1, so they have the same degree, so then I do the ratio of the leading coefficients. Alright, if I want to make it a little bit more complex, I can take this same concept, but then let's say just square each one of these quantities in the numerator and the denominator. So it didn't change any of the features. It just has a multiplicity of 2 for the 0, and we don't really call it multiplicity, but it's the same vertical asymptote of x equals 3. If I want to make this look more complex, I can multiply this out. So in this form, it's a little bit more difficult to see that I met those requirements, but I did. One other thing I could do, or one other thing I did, there are other things you could do as well. Again, the point is not to make as complicated of a problem as you can, make things as easy on yourself as possible, but just to show you. So here I have my x minus 3 in the denominator, and if I put something that's going to give me imaginary solutions in the denominator as well, this is not going to give me any vertical asymptotes or holes. But now I need to understand that the degree in the denominator is going to become cubed if I multiply this out, so I need to make this cubed. I did not multiply this out because that's just a waste of time for this example. I just wanted to show you some other things that you can do. Okay, so here's a word problem, but it kind of shows a nice application of a use of rational functions. So the Game Commission introduces 100 deer into newly acquired state game lands. The population N of the herd is given by the equation below, where T is the time in years. Find the population when T equals 5, T equals 10, and T equals 25. What is the limiting size of the herd as time increases? Alright, so again, pause the video, answer those questions, and then unpause it when you're ready to check your answers. And if you're wondering, yes, it is, for at least the first part here, T equals 5, 10, and 25, it is as simple as it sounds. So pause the video and unpause it when you're ready to check. Okay, so to find when T is 5, T is 10, and T is 25, we just plug in 5, 10, and 25. So I showed my work for the first one. You get 333 and a third. We can't have a third of a deer, so that's going to be 333 deer. When T is 10, I get 500 deer. When T is 25, I get 800 deer. Hopefully I did my math correct, and hopefully you did your math correct and got the same answers. Limiting size. So this is where we want to understand, well, what is that actually asking us? Well, that's saying, as time goes on forever, so think as T goes to infinity, what is the size of the population going to approach? So in this case, that's saying what's the N behavior. So what determines N behavior? That's going to be a horizontal asymptote. So what is our horizontal asymptote? Well, if I look back up at the function, I can see the degree of the numerator and the degree of the denominator are the same. So I divide the coefficients. 60 divided by 0.04 is 1,500. So the limiting size of the population is 1,500 deer, according to this model. That's it for these notes. So this will give you a good time to check up on, or catch up on any homework you might be a little behind on, or if you want to work a little bit ahead on the assignment for tomorrow.